Now we're going to take a look at pipe networks. So in this case, the flow actually has a split in it, and it can go one of two directions. Obviously, pipe networks could become very complicated with lots of different splits. And if you think of a standard heating system, for instance, standard boiler in the basement, it feeds dozens of radiators throughout a home through a very complicated network of pipes. Same thing with your water flow into your house. Many different loops occurring. So the water can go all different directions at different points. So we need to be able to sort of handle that. And so this is the simplest possible example of that. So you just have two possible pipes. The flow comes in here at inlet and could go up through path B or down through path A. And we're going to just analyze that one and see how that works. And this is all just algebra in the end, so it's not mathematically complicated in that sense, but we'll see that these pipe networks very quickly become very complicated just from the sheer number of variables. So this particular very simple example, we're going to have the inlet pressure. That's going to be the pressure right at the T here. So we're going to assume that the pressure, we know the pressure right where the split occurs. And then the flow could go up over here around the B network, and it passes the loss coefficient due to the corner at K1, loss coefficient at K2 on the other corner, and then back here and to the outlet, where again we're not worrying about the pressure of the turn to the outlet. We're just saying we know the pressure somehow right at the junction here. So the pressure at the inlet for both pipes is the same at A and B because we know the pressure in that junction. The pressure at the outlet for both pipes A and B is the same because of the outlet. But the water, in this case, it is a water flow. I'll put that up here. Water flow, water gets to this point, and then some of it will go up and some of it will go down, and that's what we're going to have to worry about. We'll assume the pipes are all made out of the same material, so they have an epsilon of 0.002 millimeters in this case. The pipes have different diameters, 6 centimeters for the A loop down here, 4 centimeters for the B loop up there. I seem to have drawn them actually slightly reversed. This one looks smaller than that, but anyway, 6 centimeters for A, 4 centimeters for B. The lengths of the pipes are slightly different as well. The A loop is 2 centimeters longer than the B loop. And we are going to make the assumption that all of the loss coefficients are the same. So K1, K2, K3, K4. We'll assume they're all 0.9 here. Probably that's not realistic. I mean, the A pipe diameter is larger, so that should cause the loss coefficients to be somewhat less. But anyway, you'll see that won't matter much in terms of it would be easy to modify what I show you for different Ks. That are not the challenge. We're going to try to find the mass flow rate for a given pressure. Now we know that when we have a complex pipe, that's the harder problem because the inlet pressure, if we're given that, we're trying to find U, that we have to find U in terms of pressure, but in order to find pressure, that U we have to find F, and F depends on U. So we had that whole thing where we have to circle, you kind of guess an F, calculate a U, guess another F, calculate another U, until we sort of circle in on the answer. We'll see in this particular problem that we do have to do a bit of that at first, but it turns out we don't have to do it in this case because basically F turns out to be negligible compared to these loss coefficients, but that's not always true. So that is still the concern, that we have that kind of circular behavior. These are the two. We're assuming delta Z is 0 for this problem, so gravity is not an issue. And we're assuming that the delta P here is, not assuming, this is the formula for delta P, 1/2 rho UA squared times FA LA over DA plus the two loss coefficients. So that's the pressure drop across the A, and of course the same pressure drop across the B line, but that is represented by U squared B, FB K1 plus K2. So those are our two equations that we're going to work with to get the solution. So we're going to try to find the mass flow rate if we have a 40,000 newtons per meter squared pressure difference between the inlet junction and the outlet junction. So that's what we'll do in the next lecture.